Oh, the screen is great. That's my I was like, it gives everyone rest. Yeah. Thank goodness for rest. Exactly. I think you fall asleep. Yeah, I just saw that. You see what you did wrong. She created it too. Was that? I don't know if she with the correct answer, but she showed it that was missed on it. Giving us the total grading of it. Okay. I didn't even know it was graded until I checked the Discord because I never got like an email or this. Oh, really?
Then have pots.
Yeah, I was gonna work on that tomorrow and then maybe go to like office hours. Or I mean, we're gonna play. Yeah, I think I just want to say she was like, What's that?
No question.
All right, it's 4 o'clock, so let's go ahead and get started today. All right, good afternoon, everyone. How's everyone doing today? Something good happened? I see. Well, I mean, we're close to spring break, and so we have this week, we have next week, then we get a week off, or as I like to say, a week off to catch up on work. I think that's probably more realistic for both you guys and for faculty too. Okay, so the plan for today is we're going to finish up our set of lecture slides on cardiovascular diseases and medical devices. Okay, so I think we left off in the middle of aneurysms last time, and so we're going to finish that up today. And then that's the plan. And then so we'll see if if we end early, we end early, because I think we talked about the bulk of the stuff last time. And so if we end up ending early today, then I'll just call it. Announcement I want to make. So I posted the survey. It's not really the survey, but there's a survey that's posted on Canvas for you to select which type of model you want to do for your final project. Okay, and so make sure you vote in that by Friday. And then over the weekend, maybe not over the weekend, I'm kind of busy, but or maybe early next week, what I'll do is I'll send you your image data so you can start working on the geometry for your project. Okay. So I noticed that I think everyone turned in the tutorial, and so I haven't had a chance to look at them yet, but I do plan on grading those by the end of this week. Okay? So you'll know how many points you got. But from what I've seen, from the people that did show me, I think everyone's doing pretty good on that. Question.
Yeah. What are some of the possible reasons that when you create the model, it says error, can't create the model?
I think probably the most common reason I see for people is that they have segmentations that overlap with each other. So if you're going along the vessel and you're making like the segmentations, right?
Yeah.
If you have ones that kind of cross over like this, that's usually the reason I see people errors come up. But there might be other reasons too, because I was working with someone for a while, and they had this kind of very esoteric error creating the model, and and that happens sometimes because it is a research software. And so the only thing we could really do is just kind of restart kind of the path from scratch and just kind of go from there. So it does happen sometimes, unfortunately, that's what you get for paying, a couple grad students, pizza and beer once in a while to develop your software. But, but for all those things considered, it works pretty well. I used to be with that grad student with pizza and beer that was developing the software, but I moved on in my life, and now it's someone else's problem. Okay. So I think that's all my announcements. Are there any questions I can answer before we get started? Okay, all right, so let me go ahead and skip ahead to the point where we left off. Okay. So remember, we were talking last week about the different kinds of cardiovascular diseases. And so we talked about high blood pressure, we talked about atherosclerosis, and we left off talking about aneurysms. Okay. And so just to kind of jog your memory, aneurysms are these kind of sacs or kind of enlargements of the vessels that can occur in your cardiovascular system, and they have 2 different forms. And so they have some aneurysms that can form kind of in line with the vessel, and we call those fusiform aneurysms. And there are other types of aneurysms called saccular, which kind of form on the sides of the vessel. Okay. Sometimes the saccular ones are called like a berry aneurysm, because it literally looks like a berry kind of forming off to the side. Okay. Although it's not a berry that you want to pick, you kind of want to leave it alone most of the time. Okay. And we were talking about cerebral aneurysms, and so cerebral aneurysms are a very common place where aneurysms can occur, and that's in your brain, and they're mostly of the saccular variety. Okay, and remember we talked about the scary thing about these cerebral aneurysms is that most people that have them have no idea that they have them, just because it's hard to justify getting a scan up in your brain. Okay, and so most of the people that have them, they have no idea just because they never get scanned, but they're also harmless in most of the people too. But in those very rare cases where the aneurysm does rupture, it unfortunately leads to very catastrophic consequences. For those people, they kind of have no idea that it's coming. And so it kind of comes as a really big shock for a lot of people, which is kind of leads to aneurysms being kind of a very hot topic of research, both in the modeling community, which is kind of what we're doing in this class, but of course in the medical community as well. And so better ways to kind of detect it, better ways to prevent it, and better ways to help treat people that do have an event. Okay, so I think we kind of left off here. So we're talking about the fluid mechanics inside these aneurysms, and I don't want to repeat everything on the slide, but I think the big concern with these aneurysms is that the flow tends to slow down inside these aneurysms compared to flow in the regular vessels. Okay, and that's especially true for these saccular ones, which kind of exist off to the side. And so I know these images make it seem like you have flow that kind of gets drawn in here and it circulates. But if you look at it in reality, it's difficult. It's difficult for blood or any fluid to come get sucked into like a side thing like that. And so, these images are a little bit misleading because it makes it seem like the velocities are higher than they actually are. But if you were to compare, the magnitude of the velocities, you probably have most of the flow that's coming in, going through the vessel like normal, and only a small percentage of it actually gets sucked into the aneurysm. Okay, so the exact amount and the exact amount of flow, exact velocities, of course, depends strongly on the geometry. But it's not surprising to have flows that are maybe like 1/10 or even less of the main vessel flow going into the aneurysms. Okay? And that's a problem because what happens then is because you have such low flow here, what can happen is that the blood can stagnate inside these aneurysms. And when you have stagnant flow or stagnant blood flow, those are the kinds of blood flows that tend to clot. Those are the ones that tend to weaken the vessel wall. And so all kinds of adverse effects can happen. And so and so I think I'd say at this point, at least from last time when I did kind of a really deep dive into the literature, we're still kind of really studying this and seeing what the effects are from a biological point of view. Okay. And so I think this is where we left off. And so, one of the primary, medical concerns about aneurysms is their rupture. Okay. And so, if aneurysms didn't rupture, I think we probably wouldn't care that they existed at all. Right. And so they're just kind of nice. They're kind of a little bit of enlargement of a vessel, but if they're not going to cause any harm, there's no reason to do anything. But, but because they tend to rupture and because they cause, internal bleeding whenever they do rupture, that's why there's such an intense, medical concern over these aneurysms. Okay? And unfortunately, there's lots of different theories about what's causing this. And so there's people in the community that think there's a very strong correlation with fluid mechanics. So some people think there's high wall shear stress that causes it. Some people think that low wall shear stress leads to aneurysm rupture. Some people think that it doesn't have anything to do with fluid mechanics at all. Some people think it's purely chemical, purely biological, and no one has really stepped forward in the community to really kind of give definitive evidence or definitive data, definitive proof of one theory over the other. And so, it is still very much an area of research. Okay. And so when you hear things like that, on the one hand, it's exciting because if you want to jump into this field, you want to contribute in research. There are problems like this that could use more brilliant minds, right? More people gathering data, more people postulating theories. And so that's exciting from a research point of view, but from a medical point of view, it's scary, because if you end up getting one, or if a loved one of yours ends up getting an aneurysm, it's I wouldn't say there's a clear picture of what you should do. And I think that's especially true when you start thinking about how to actually treat these. Okay. And so let's say that you have an aneurysm in your let's say it's in your brain. Okay. And there's a concern whether that aneurysm is going to rupture or not. And so if the doctor actually did want to go in and treat it, there are options for it. And some of these procedures have been successful. But with that said, they do carry a lot of risks. Okay. And so two of the more common ways to treat these cerebral aneurysms, number one is clipping. And so what they literally do is it's not literally a paper clip, but it might as well be, is that they go in. And so let's say there's the aneurysm here. And what they want to do is they basically want to prevent any blood from entering the aneurysm at all. Because what their logic is that even if it ruptures, then there's nothing really that's going to come out because it's going to be separated from the main flow. And so what they literally do is that they take the head or take the neck of the aneurysm and they just clip it off. Okay, they don't cut it out because that's that's normally very dangerous to cut out tissue inside the brain. You have to be very delicate for that. But what they can do without too much risk is to just apply a clip right there to cut off the amount of flow that's going. Okay. So that's treatment option number one. Okay. The other option, which I think is becoming more popular nowadays, is a method called coiling. Okay. And so another train of thought, for treating these, kind of with the same logic as the first one, because ideally you want to cut off all the blood flow that's going into the aneurysm, is to put in like literally a metal coil that kind of snakes all the way around the around the aneurysm. Okay. And what's special about this wire is that it's coated with a particular substance to encourage blood clotting, basically. Okay. And so what you do is you insert this coil in there, and it kind of messes up the flow patterns inside there, and biologically it also encourages it to clot. Okay. And so effectively you get the same thing where you get the entire aneurysm to clot locally. Okay. And so if the blood clots here, then it effectively becomes a solid, and again you don't have any blood flow that's going inside. Okay. And so that's another popular option because it's a little bit less invasive, because for clipping you kind of have to open up the entire skull and you have to go in there and clip it from the outside. With coiling you can go in from the inside, and so you can actually treat it with a wire that snakes up from somewhere else in your body. And so I think just that prospect is making coiling a little bit more popular because it's a little bit less risky. But with that said, anytime you're doing any kind of surgical procedure on the brain, it carries an immense amount of risk, right? And so your tissues, your brain, there's just so many nerves up there, and if one thing goes wrong, then it can lead to really bad outcomes, even sometimes even worse than the aneurysm rupturing to begin with. Okay. All right, question. So is there a difference between the material properties of the brain blood vessels and the blood vessels found in the rest of the body? Yeah, that's a great question. And that's definitely one of the theories that's been put forward too, that some of the material properties of the blood vessels up there, there are differences. And so the amount of elastin, the amount of collagen, it is different there. And if I remember correctly, I think it generally has a little bit more collagen, a little bit more elastin than the rest of the body. So those blood vessels are actually a little bit more flexible than others. That's one theory about why people think that it tends to kind of balloon up there, because it is more flexible. Yeah. Mm-hmm. And so because these operations have an immense amount of risk, it's not an easy decision for doctors to go in and operate whenever they see a cerebral aneurysm. Okay. And so right now, kind of what the criteria is that if the doctors see an aneurysm on a scan and it's not too big, they might actually just choose to leave it alone, because what they say is that it's more risky. It's riskier for us to go in and do something about it than it is for the aneurysm to rupture. Okay. But of course, there's a lot of gray areas in that too, and so it's a big concern. And so in some sense, sometimes it's better, for a lot of people to not even scan up there, to not even see, so that they don't have to make this tough decision, right? Because it is a tough decision. All right, any questions on this? Okay, and so you can form aneurysms in other parts of your body, and so another common area to form aneurysms, very different anatomy, is in your abdominal. Okay, and so in your abdominal, just like we've all seen from this vascular tutorial, you have a big blood vessel that goes down to your legs, right? And that blood vessel is your aorta. And so what can happen sometimes is that the kind of the descending part of the aorta can really kind of blow up like this. Okay. And we call those AAAs, so abdominal aortic aneurysms. Okay? And so in contrast to the cerebral ones, these tend to be in the fusiform variety. And so these kind of blow up in, within line of the vessel. So you don't have any sacs that kind of form. Right? But just like cerebral aneurysms, these tend to be asymptomatic. And so, most people don't even realize that they have them, until it's kind of too late. Okay? But just like cerebral aneurysms, they can rupture and they can lead to internal bleeding and death. Okay. And if they are detected, again, the decision to treat, once again, it depends on the size. And so the bigger it is, generally the more dangerous it is, and that's when the doctors are more likely to operate. Okay. Question.
How are they supposed to treat the fusiform variety versus like the sacral? Like I get you could put something in there and flip it, but how would you do something like this?
Yeah, no, it's a good question. It's definitely a lot more complicated, especially because this vessel is a lot bigger too. And so what I've seen is that they've inserted people, they'll insert a graft inside the aneurysm. And so what that is basically an artificial blood vessel. And so they kind of like stick that inside the aneurysm so that the blood just flows to the graft instead through the aneurysm part. Yeah, and I've seen some where they just kind of take it out completely too, and then kind of replace it with the blood vessel there. So it's a big deal. And so that's why these if you can avoid an operation for these things, that's probably ultimately going to be a good thing, for your long-term health. And something that's unique about the AAAs is that they can form this substance called the intraluminal thrombus, or ILT. Okay. And so it's a kind of blood clotting, but it's kind of a special kind of blood clot that kind of only forms in these AAAs, where it's a lot more fibrous than normal blood clotting. Okay. And the weird thing about this ILT is that it's still kind of alive, and so it actually, once it starts to form inside these AAAs, it actually it kind of leaches a lot of the oxygen and nutrients that's meant for the other parts of the body. So it kind of almost becomes a leech inside there. And so I do have images of this ILT on the next slide, but it is a little bit graphic, and so if you're a little bit squeamish, I am going to warn you. Okay, everyone ready? Okay, so here are some images of the ILTs. Okay, and so it looks gross, and so I look at this and I actually get really squeamish from these things too, and so I can't look at this for too long, but this is kind of the idea. But you can see here that it's a clotting kind of material. So here's kind of a good image on the bottom right, and so it's not kind of liquid blood, but you can see it's kind of the solid kind of mushy kind of substance, and that's kind of the thrombus that forms in these AAAs. Yeah. Okay, let's move on. Okay, so let's talk about initiation, growth, and rupture. Okay, and so just like cerebral aneurysms, there's a lot of research going into saying how do these aneurysms initiate, how do they grow and how do they rupture? Okay, but there's still not that many conclusive results yet. But what researchers have been able to find is that when these do rupture, it's due to the vessel basically losing a lot of its material strength. Okay. And so that usually occurs through the loss of elastin. And some of that happens due to the ILTs too. And so the ILTs can kind of, take away some of that elastin or take away some of that strength. So then the vessel wall actually, breaks from that. And some causes that have been proposed by the community is that aging might play a factor. And so you tend to see AAAs in older patients. Okay. And also the wall shear stress, how the endothelial cells respond to the wall shear stress has been proposed as a theory as well. But, it's still very much an area of research. Okay, any questions on aneurysms? Yeah, I hate to present this in the class as something that this is what we know, but there's still a lot to learn. It's not a satisfying thing to present, as an instructor, but I've kind of gone back and forth a lot about whether to include aneurysms, but they are such a big area of research, and from a computational point of view, we can actually simulate them. And so this is actually an image from one of my colleagues that did a lot of research on this in graduate school. And so it's something that we can research, and so in the end I decided to put it on, but it is something that we still need to learn a lot about before we can really do anything really about it. Okay, so that's enough about cardiovascular diseases. So now let's talk about medical devices. And so medical devices, I think, is a term that is becoming a pretty hot term, among the growing community of engineers, because a lot of people are trying to get into this industry, which is great, because I think the more great minds, the more people that are working in this industry means that we're going to develop much better devices, than we have right now. Okay. And so medical devices is kind of a general term that is used to refer to any kind of device that you can manufacture, out with your hands outside, that are used to treat or manage any kind of disease. Okay, but of course, for this class, we're going to focus on the devices that that treat cardiovascular disease. But there are some other devices out there as well. Okay, and so with this kind of comes a caveat that every day we're developing and getting better at treating and managing cardiovascular disease, and because of that, our life expectancy tends to go up. Okay? But with that comes a larger volume of people who need these kinds of medical devices, and so it definitely is a hot industry to be in, because the demand for these devices is kind of growing every day, especially as our population gets bigger. Okay? But with that said, a medical device is usually not the first thing that you're going to try. And so if you come to a doctor with some kind of disease, first thing they're going to try is some kind of drugs or some kind of medicine. Okay, because usually this is the least invasive and also the least costly thing to treat your disease. And so it's only after the drugs and the medicines are unsuccessful, that's when doctors will start to prescribe maybe surgery we need, or maybe we need to implement a medical device. Okay. And so for this class, we're going to work with kind of a more specific definition for medical devices, is that it's any kind of device that's implanted in a person's body to help them treat or manage cardiovascular disease. Okay? And so for the rest of class today, I have some of the more common ones that are used to treat cardiovascular disease. And so we're going to talk about how they work and what are some of the challenges related to them. Okay. And so before we do that, we have to break them down into different categories. Okay. And so, there's been a ton of different medical devices out there that have been developed, and they're developed for different types of diseases. Okay. But there are two broad categories that I want to go over. And so the first type are active devices. Okay. And so these devices are unique in that they require some kind of power source to operate. And so they need to be, in other words, they need to be charged, and they need to be, actively working through the whole time. That presents some really interesting logistical challenges too. But the other type of device, and the one we'll focus on more, are passive devices. So these devices don't have any energy requirement, and they're kind of just more passive structures inside the system. Okay. And so the image I have on the right there is known as an LVAD. And LVAD stands for left ventricular assist device. And so this is one of the more, I would say, the more extreme devices that you can put inside your body, and this is basically an external blood pump. Okay. And so for people with weak or failing hearts, or more commonly for people that are awaiting a heart transplant, these people can get this kind of device. This is an active device. Okay. And so it requires energy to pump the blood. And what this can do is it can provide kind of support for a failing heart to kind of push blood throughout the body. Okay. Okay, so the first type of device that we'll go over, this is the simplest one that you can have. It's called a vascular graft. Okay. And so a vascular graft is essentially just a tube, right? And so we talked about the cardiovascular system as basically like plumbing, essentially. And so a graft is like a spare tube or a spare blood vessel. Okay. And so, the hard definition for this is that there's basically an additional blood vessel that can be used to repair, replace, or bypass a diseased vessel inside a person. Okay. And so there are two different kinds of grafts. Okay? And so there are biological grafts. And so those are grafts that are harvested within the same person. And so I'd say that's probably the most common type of graft that you see today. And so what they basically do is that they take another blood vessel from another part of your body, one that's redundant, one that you can obviously live without, and then they put that blood vessel somewhere else in your body to help support your circulation. Okay. So one of the more common ways that this happens is for bypass surgery, right? As we talked about bypass surgery last time. And so if you ever need to bypass, blood, to a certain part of your heart, oftentimes they'll take a blood vessel from your leg, and then they'll stick that inside your heart. Okay. And so that procedure I'm actually pretty familiar with. That's something I studied a lot in graduate school. And so that's kind of a really interesting application of that. Yeah.
With different vessels from different part of the body have like different structure.
It does, yes. Yeah, and that's one of the main challenges for it too. And so the blood vessel that they harvest from the leg, it's actually not an artery, but it's actually a vein. And so the vein, veins structurally are very different from arteries. And so first of all, veins have a lot of these little tiny valves inside them, just to kind of help with the circulation in the veins. But if you try to put that in an arterial system, it might actually clog the blood. And so what they do is that once they take the vein out, they flip it backwards, and so the valves are facing the other way, and so blood can actually go through. But even then, there's a lot of issues with it, because the vein is usually not used to the high amounts of flows and pressures that are on the arterial side, and so that tends to make them maladapt. And so you have blood clotting, and the blood vessel wall might kind of thicken up too much too. And so that was one of my big research projects in grad school, because what they found is that the vein grafts, they work pretty well within 4 or 5 years, 10 years of surgery. But after about 10 years, half of them will fail, and then the person needs to go back in for another bypass surgery. And so, what the doctors are interested in is that, can we use simulations, to learn anything about these grafts to better improve them. Yeah, so that was probably one of my biggest projects in grad school. And so the other type of graft that we have are known as synthetic grafts, and these are just like the name implies, these are grafts that are made inside the lab. And so these are not harvested from inside the body, but are kind of specially crafted inside the lab. Okay. So conceptually, they seem simple, right? And so it's basically just a spare tube. And so, it feels like you can just go down to Home Depot and get a graft from there. But there are a lot of biological challenges that are associated with these, and they have to do with an issue called suitability. Okay. And so, just like I just mentioned, for biological grafts, a lot of times blood vessels are going to be put in a situation where they're not used to. And so because of that, they can undergo a process known as maladaptation, where basically they either the body attacks them, or they might react negatively and end up blocking the flow and causing more harm than good. Okay. And synthetic grafts kind of have the same issue. Synthetic grafts have the additional challenges that the body often doesn't recognize the material that's used for these synthetic grafts. And so what can happen a lot is that the body will actually start to attack these synthetic grafts as well, leading to blood clotting. It can lead to the buildup of platelets of white blood cells, and so again, it might end up doing more harm than good. Okay. I think ever since I graduated, I think there has been some advancements in synthetic grafts. But another challenge in the medical community is that it's traditionally very, very conservative in trying out new technologies. And so, even if you can develop a great graft in the lab and show that it's good, it takes a while. And so the barrier that you run into then is that it takes a while for doctors to actually adopt it. Okay. And this is true for any medical device too, because doctors and surgeons are notoriously very conservative, and so they don't really like to try anything new, which is understandable, because I mean they're dealing with people's lives, right? And so you don't want to try something new and have someone's life, have someone pass away because of your decision, right? And so it usually takes a long time for even the newest and best technologies to gain a foothold in the medical community. All right, any questions on this? Okay. All right, so now let's talk about stents. And so stents, I think, is a popular device. And so a stent is basically, you can think of it as an expandable tube, okay, that is inserted into an artery to correct some kind of narrowing or to support the structure of a vessel wall. Okay. And so what it looks like is here on the right. And so if you look here, we have this wire that's coming through this blood vessel, but it's surrounded by this kind of wire mesh, right? And so what will happen is that once the mesh is kind of put into place, okay, and it's a little bit hard to see, but if you look on the walls of this vessel, right, we have some atherosclerosis here, right? And so it's highlighted in yellow to kind of emphasize the fact that it's plaque, okay? And so what's going to happen is that once the stent is kind of put in place right here, there's a inflatable balloon on the inside that kind of inflates and kind of pushes the stent into the plaque, okay? And the idea is literally to, if you have kind of a narrowing of your blood vessel, to expand the stent to kind of smush that plaque to the side, okay? And so for cases where you have, atherosclerosis, or you have some kind of narrowing, and it's only in one vessel, stents are a great option to kind of, give your body some relief, give your body some, some flow support. Okay, and it's relatively non-invasive because it can be applied with a catheter, and so you don't have to open up someone's chest in order to do that. So that's that's really nice. Okay. Okay. All right, and so I think the next slide here is I have a video. Okay. Yes. Should be a video. Come on. Let's do this. Let's go to YouTube and we'll search up stent deployment because it is pretty cool. I don't think Zoom has sound, but you don't really need sound for this. Okay. There we go. Here's the video that I wanted to show. Okay. Okay, so here you have kind of a very diseased blood vessel, right? And so what's literally happening is that you insert the stent and then it's expanded to kind of smush the plaque on the outside. Okay. But the interesting thing is that the stent actually stays inside the vessel. Okay. Because what the concern is that if you take the stent out, then the plaque will just kind of just come back in. And so you need to leave the stent in there to kind of prevent that plaque from kind of growing back into the vessel. Okay. See one more time. And so it expands, and so you can see afterwards the catheter is removed, but the stent is still left in place. Okay. Yeah.
Did you ever need to replace that material after a period of time? Yeah,
it's a great question. And so
do you have high blood pressure?
No, I don't.
About the danger of a stroke or heart attack.
That scared the crap out of me. Sorry about that. Okay. So the question is, do we ever need to go in and replace this? And so the hope is that you don't. And so these stents are designed, and so what you'll see on the next slide. Okay, never mind. So I think it's on the next slide. Yeah, and so what you'll see on the next slide is that these stents are made of a certain kind of metal, which is designed not to corrode over time. And so the idea is that you can put the stent in there, and it can stay in there for a really long time. Okay, because it's even though it's considered minimally invasive, it's still invasive, right? And so you typically don't want to be sticking wires inside your body too much if you can avoid it. And so these stents are designed to last a very, very long time. But with that said, there are complications that can occur, and if they do, it's actually really scary because if they do have to either replace it or take it out for some reason, it's not an easy thing to do, because once these stents are kind of designed to only expand. Once they kind of expand, they're not really designed to contract it. So getting a stent outside of the blood vessel is normally very, very difficult. And so the hope is that once you kind of expand the stent, it's kind of in there for the rest of your life. And hopefully there's no kind of complications that occur from that. Okay. But with that said, there is research being done on this idea of a fully resorbable stent. Okay. And so this would kind of, eliminate that concern. Whereas like if you expand a stent inside the body, then it would only be there for a certain period of time, maybe a few months or a year or something like that. But it's made of a special kind of material that would kind of biodegrade over time, or maybe it gets absorbed into the blood vessel wall, and then no longer cause any complications. But that's very much still like a it's still in the lab, and so it's not even close to. Last time I checked, it's not even close to becoming a thing in people yet. So we're still a long way away from that. Okay. Yeah.
If that causes the way it looks, is that how it really looks like?
It does. Yeah.
Because it looks like it's going to cut up the plaque in pieces.
Yep. Yeah, no, it's a concern. Yeah, and so this is not the only shape, and so there are some. I mean, this is a fairly coarse, I would say, coarse pattern, and so there are some out there that with a much finer pattern, where the concern for kind of slicing and kind of breaking the plaque is a little bit less. But there's all different kinds of shapes and sizes that they can choose for the stents to kind of eliminate these, and it's usually the doctor's call to say what kind of stent that they use for a procedure. Yeah. And part of their concern is, how, the risk of rupture for the plaque. Yeah. Yeah.
Has a plaque built onto it?
It can, yes. And that's the scary thing too. So for not a lot, for some patients, you know, even after you kind of push the plaque off to the side like this, the plaque can actually start to form on top of the stent. And so then you kind of have a double problem because, you know, you can't really push that plaque to the side anymore because there's already something metal on the inside there. And so that's a pretty dangerous situation. And so if that happens, then your only option really is to do a bypass. And so to kind of go around that blockage. But it does happen, and it does happen, you know, not a lot, but not an insignificant number of times. Yeah. Okay, so let's talk about these complications. So these are kind of the two main concerns that doctors have when deploying a stent. And so the first is, you know, just like you know, the question that was asked about restenosis. Okay, and so you know, there's a concern that after you deploy a stent, you know, the blood vessel might kind of get clogged up again. Either you have plaque that forms on the outside of that, or sometimes, you know, for certain cases, this is pretty rare now because, you know, we've gotten a lot better at deploying these. But if you have an operator that's deploying your stent that is not very skilled, what can happen is that it might not expand, you know, expand correctly. And what can happen is that the elastic recoil from the stent can actually cause it to kind of plug up, but it's even worse because it'll kind of take the blood vessel wall with it. But you know, this is more rare nowadays because now we've learned a lot about proper stent placement, and we know, you know, how to do this properly without that happening. But the risk of, you know, plaque forming on the outside of the stent is still there for sure. Okay. The other concern that can happen is that you can actually injure the blood vessel wall, and so you know, if you guys saw from the animation, right? So when you have the stent expand, you know, you're kind of doing a pretty big smushing kind of procedure, you know, kind of depending on the severity of the plaque. And so if you do this kind of too quickly, and you do it in a way that the vessel is not really expecting it, you can actually injure the tissue that's involved in the vessel wall as well. Okay. And if the injury is severe, then the body might actually react to it and cause, you know, again, it caused some narrowing and it caused some blood clotting. Okay. And so this phenomenon here, where you damage the tissue of the vessel wall, which is not unique to stenting, but it can happen in other cases. But, you know, think about it if you injure another part of your body, right? So let's say that you sprain your ankle, or you kind of strain your a muscle. Okay. Your body's natural reaction to that is to kind of, you know, flood that area with blood, with cells, and the whole area kind of becomes inflamed and puffed up, right? And so, you know, when that happens inside your blood vessels, it causes a what we call neo-intimal hyperplasia, okay, or short term is NH. Okay? And so if you cause NH, if you cause some kind of injury with the stent, then it can cause your body to react to that injury. Okay, and of course that's not a good thing. Okay, so I kind of showed this slide a little bit already, but I did want to talk about the two main types of stents. Okay. So besides geometry, and so, you know, so there's lots of different types of geometries of stents out there. There's different kinds of materials that can be used as well. And so the first type of material is just to use straight up metal. Okay, and so those are called bare metal stents. And the type of metal that they use is a certain alloy of steel, or certain called 316L steel. Okay, and so what they found is that this metal here has, you know, the best kind of material properties, and so it's rigid enough, and so that it won't, you know, it won't collapse on itself later on. And it has very good anti-corrosion properties as well. Okay. And it's known to also have good compatibility with the body as well. And so your body, you know, it doesn't really hate steel all that much, and so it'll kind of leave it alone. Okay. But the more common type of stent that's used nowadays is called drug-eluting stents, or DES. Okay. And so these are kind of a twist off the bare metal stents, in that these stents are again made of steel, but they kind of coat it with the drug to kind of you know, to kind of prevent a lot of the complications that can occur. Okay. And so the coating that they give, you know, it kind of discourages your body from attacking it. It kind of discourages the body's response to it. And so if you do end up injuring the vessel wall, then the drugs that are coated on these stents can help inhibit kind of the body's response to it, which is, you know, ultimately going to be a good thing. Okay. And so because structurally the drug-eluting stents are not that different from the bare metal ones, they're being used a lot more often, because the drugs, you know, because they're kind of seen as a useful feature. They're going to prevent a lot of the bad stuff from happening. And so that's why drug-eluting stents are becoming more and more common nowadays. Okay. And so here on the right, you can see kind of an image of that happening. So you can see these little red particles. They kind of represent the drug that's being coated onto the stents. And so once the stent is expanded, then those drugs can kind of penetrate into the vessel wall and into the plaque. They kind of prevent any kind of either restenosis or any kind of injury response from the body. Okay. All right. Any questions on stents? Okay, so let's talk about artificial heart valves. So this is pretty cool actually, and so this one actually is hits pretty close to home for us because I'm sure everyone is aware of Edwards Life Science down in Irvine, and so a big part of the Irvine branch or Edwards is that they work on artificial heart valves, and so I was fortunate enough to get a tour of Edwards a couple times actually, and I looked at some of the work that they're doing, and they're doing a lot of cool work with valves, and so if you want to work at Edwards down here, then valves is primarily what they do. They do a lot of other stuff too, but valves is kind of their main thing. Okay. And so let's kind of recall what a heart valve is. And so a valve is basically used inside the heart to to control the amount of flow. Okay. And so what they do is that they ensure that the blood only goes a certain direction in your heart, and when the blood tries to come back through the valve shuts and it prevents the blood from coming backwards. Okay. And so the main geometry of the valve, you can see it kind of really well in this image right here. Okay. And so valves are comprised of these structures known as leaflets, okay, where they kind of really look like kind of petals of a flower, kind of think of it like that. And so they're kind of a flexible kind of material. They're flexible, but they're also very, very strong as well. And so what can happen for a lot of people, and this is more common in older people, is that these valves can get diseased. Okay. And if they get diseased, they can lead to adverse effects. And so some of the different kinds of valve disease that you can have, stenotic valve disease. Okay. And so in stenotic valve disease, then the leaflets become a little bit too stiff. And so if they get too stiff, then they don't really open or close properly. Or another type of valve disease is a regurgitant valve. Or more informally, you can think of this as like a leaky valve. Okay. And so leaky valves, they don't close properly, and so they tend to leak flow backwards when they should be preventing that from beginning. Okay. And so both of these types of disease are bad, and so if they get to a certain point where it's really affecting the person's health, then you have to go in and replace them. Okay, and so what you replace them with is an artificial heart valves. Okay. Replacement valves, they're not too different from like a valve that you would think of in like a fluid mechanical system. But of course, they have to be designed, to work inside the body. Okay. And so the number one thing that valves have to be is that they have to be very durable. And so, and of course, this depends on your heart rate, depends on the person. But within a year, these valves are expected to open and close about 40 million times per year. Okay. And so that's a lot. And they never stop too. And so, as long as your heart's still beating, your valve should still be working. Of course, just like any other device, they're expected to be non-thrombogenic. And so they're expected to not cause the blood to clot. And they also are expected to have a large orifice area as well to let blood through. And there's two main types of valves that are currently available. And so the first type of valve is known as a mechanical valve. And so these mechanical valves don't look that different from a valve that you would see in a fluid system. And so a lot of the earlier valves look like that. And a lot of the current valves look like that as well. Okay. And so these are made of some kind of metal type of material. Okay. The other type of valve is known as a biological valve. Okay. And these are kind of specially constructed from animal tissue, and they're supported on a frame. Okay. And so they look kind of like what's on the right. And so these kind of, at least visually, more closely resemble what you would find in your body. But actually performance-wise and kind of body compatibility-wise, both are pretty good. Okay. All right. Any questions on this so far? Yeah.
Would these valves like limit like type of physical activity they do?
It would, yes. Yeah. And that's true for kind of any kind of device that you get input into your body. So you get a stent, you get a graft. the doctor, the first thing the doctor is going to tell you is to kind of, don't push yourself too much, at least until you kind of get used to it. And so, yeah, and so there's definitely a period of like, your body has to get used to this, and you don't want to increase your heart rate too much until you get used to it. Yeah.
How much is that?
How much? That's a great question, actually, because it's the cost that you end up paying is always a lot more than the device.
Right.
The device itself is usually not the primary cost. The primary cost is you're probably going to pay the hospital, you're going to pay the surgeon, the anesthesiologist, but hopefully, your insurance pays a lot of that, and so they kind of hide that cost from you as the consumer. But yeah, it's significant. We'll say that. Yeah.
From what I researched about how much it costs, like there's the quality of the heart valve can also differ. The highest I've seen so far is 4,000, and for the operation itself, I heard somewhat of 50K.
Yeah. Yeah.
So
That sounds about right. Yeah, because the surgeon, the surgeon makes a lot of money. I mean, and they should, they have literally people's lives in their hands, and you have to pay their entire staff too, like all the nurses, all the techs, anesthesiologists, things like that too. So yeah, that sounds about right. Okay, and so to actually implement a valve, they actually have to do a valve replacement surgery. Okay, so very, very descriptive thing. Okay, and so it's interesting because like I'd say we've actually gotten really good at this recently, and so a lot of people don't really think about how serious this is. But in order to put a new valve in there, you have to take the old one out, and then after you take the old one out, you have to put the new one in there and kind of sew it in place. And so it's a pretty major surgery, actually, if you think about it. But we have gotten really good at it recently, and so there's a procedure called transaortic valve replacement, or people call it TAVR. Okay. And the idea of TAVR is to replace a valve. I think it mostly just works for the aortic valve, because that's kind of the one that's easiest to access, and they can do it all non-invasively. Okay. And so what that means is that they can just do it straight from a catheter. So they don't have to open your chest up. They don't have to do open heart surgery. They can do it all at the end of a catheter. So that's huge. And for a long time, this is all that everyone wanted to talk about in the cardiovascular community, just how cool TAVR was. And if you could do TAVR, you were kind of part of the cool kids crew. And, because it is pretty significant. I think it's one of the more, I'd say, more significant medical advances that have happened, in the last, 20 years or so. So, yeah, so it is really cool. And it saves people a lot of money. And it saves people from a lot of risk as well, because you don't have to open up your entire chest to replace a valve anymore. Okay. And so that's the medical side of valve replacement. But what about the engineering side? Okay. And so for I would say for people like us in this class, we're probably more interested in how we can actually design the valve itself. So what are some considerations that are used when designing these valves? And so ideally, these valves, should provide as little flow obstruction when they're open. Okay. And so when they're open, they should, let as much blood through as possible. Okay? Some obstruction is required just because of the nature of the device. And so it's never going to be a fully open kind of pipe, but you want to limit the amount of obstruction as much as possible. Okay. And so similarly, it's also ideal for these valves to not be leaky, and so they shouldn't be regurgitant at all. Okay. But with that said, some regurgitation is required, just because the valves kind of have to sweep open, and then when they sweep close, it kind of takes some blood kind of back with it as well. Okay. And some valves, and I'd say this is more common for the mechanical valves. There's some gaps that are actually, built into the sides of the valves as well, that will leak. But that's on purpose. And so the purpose of those gaps is to basically prevent blood from clotting, which is a more serious issue than a little bit of leaking. Okay. And so, valve performance is very much an active area of interest for the companies that design these, and also from the research community. And what's becoming more common is for people to use CFD or some kind of simulations to assess the performance of these valves. Okay. One of my good friends actually did this as part of her work. And I'm trying to get, so she works for the FDA right now. So she does medical device regulations. So I'm trying to get her to come to this class to give a talk. But we're still kind of working out the details for that. So hopefully she can come for the last week of class. Okay? And another important thing is that the valve should be energy efficient as well. And so they should open up without really much resistance and close without much resistance as well. Okay, because if it takes kind of a lot of energy for the valve to open, then basically the structure in your body that's gonna take on that energy cost is your heart, of course. Okay, and as with anything in the body, you want to reduce the amount of load that's placed on the heart as much as possible to make sure that it lives for a very, very long time. Okay. Let's talk about complications. Okay. And so just like any other medical device, the primary concern for these valves is preventing blood clotting. Okay. This is always a concern whenever you're putting something foreign inside your body. Okay. And so for a lot of patients that do get a replacement valve, they have to take medicine known as a blood thinner, that will help prevent blood from clotting. Okay. And so, if you're not familiar with blood thinners, they're basically a medicine that you take to basically lower the viscosity of your blood. Okay. And so it makes your blood, less sticky. You can think of it like that. Okay. And so that's a requirement for a lot of these devices, but you have to be careful taking blood thinners too, because they're inhibiting the blood clotting response, your wounds and your injuries are not going to heal as well as before. The joke, it's a morbid joke, but the joke that a lot of surgeons often tell their patients that, don't go scraping your knee when you're on a blood thinner, because you literally might bleed to death from a scraped knee if you're on blood thinners. And so, it's a morbid joke, but it is true, because normally when you scrape your knee or you get like a paper cut or something, then what prevents it from bleeding anymore is that the blood clots. But if you're on blood thinners, that can't really happen. So you have to be really careful about what kind of activities that you undergo. Okay. A concern used to be about the structural integrities of the valves, just to make sure that it can open and close as often as it does, but that tends to not really be a concern, because we've kind of figured out how to make these valves last and durable all this time. Okay. And so a lot of the research now, both from the commercial side and from the academic side, is focused on different ways to kind of improve the implementation. Okay. And also to have better CFD modeling so that we can better assess valve performance as well. Okay, any questions on valves? Okay. All right, so let's talk pacemakers. And so pacemakers are a little bit of a unique one. And so it's a little bit different than the other devices that we've seen, and that pacemakers don't really have anything to do with the fluid mechanics. Okay. And so what pacemakers are is that they're devices that can apply a small electrical current or a small electrical charge on the surface of your heart to help regulate the heartbeat. Okay. And so, this is primarily used to treat heart conditions that have an irregular heartbeat. So things like arrhythmia or things like abnormally slow heartbeats. Okay? Because normally the way your heart beats is that your brain sends a signal, electrical signal from your brain down your spinal cord to your heart. Okay. But sometimes that signaling can get kind of messed up. Okay? And that's what leads to some of those irregular heartbeats. Okay. And so what you can do is you can have a pacemaker that kind of regulates these impulses to make sure that they fire appropriately. Okay. And so relative to some of the other devices that we've seen so far, pacemakers are very stable, and there's not really that much research going into pacemakers right now, because we've kind of figured them out at this point. And partially also because it's really easy to detect an abnormal heartbeat as well. And so a doctor, all it needs is a stethoscope. And so the stethoscope, he puts it onto your heart, and you can kind of tell right away that if you have an irregular heartbeat, and they just put you on a pacemaker, and then you're kind of good to go from there. Okay. So what's interesting is that some of the really old versions of pacemakers, they would actually apply basically electrical wires directly onto your skin, and because it's being placed on your skin, the charge on the electrical impulse has to be relatively high power, because the charge has to penetrate to your skin and get to the heart. But for some people, that charge was so high that it could actually cause burns and some kind of other nasty stuff on the skin too. And so now we figured out better. So now we know that we can implant the pacemaker directly onto the heart, and so the power is a lot less, and there's less risk for burning. Okay. Any questions on pacemakers? Okay. Oh yeah.
Yeah, what are the chances that the device fail and then instead of pace the heart, it just deregulated?
Yeah, no, it's definitely it's a concern, but I'd say nowadays it's very, very low. And so these devices are made, almost perfectly. And so, there's almost no risk of that happening. Our questions: how long do they typically last? Yeah, that's a good question, actually. And so this is actually, I didn't put it here. So this is actually one of the active devices. And so unlike the previous 3 devices that we saw, this is something that needs to kind of generate, it kind of utilizes power and kind of, it kind of does that. It kind of uses that power to generate those electrical impulses. And so for a lot of these devices, I know that a lot of them are charged through induction. Okay? And so, you've probably seen those wireless phone chargers where you kind of put your phone onto a platform and charges your phone. These pacemakers and these devices are kind of charged the same way because they're literally implanted inside your body. And so, the way that you charge them is you kind of plug something into a wall and you kind of sit next to it, and then it charges from the outside. As for how long they last, I'm actually not too sure. Because of course, just like any device, a lot of the electrical leads and stuff can wear out over time. And so, I'm not sure what the overall life is, but I would say it has to be at least 10, 15 years, I would say. Because I have heard of cases where, doctors have to go in and either put a new pacemaker in there or replace an old one. But, of course, that shouldn't have to happen all too much. And so, they're designed to last for a long time. Okay. So next, let's go over ventricular assist devices. And so this is the device that I showed kind of at the beginning of the medical device unit. Okay. And so these VADs are basically blood pumps that you put inside your body. Okay. And just like I mentioned before, these devices are used to support, people's with a weak or failing heart. Okay. They can kind of buy someone a bit more time. So these devices, it's, even though they look, visually, I think they kind of look kind of the coolest. And, you would think a blood pump is something that is used a lot. But these devices are not meant to be used for a long time. Okay. And so, these are only really meant to provide temporary support. Because, the longer you kind of use a device like this, where you have kind of a large amount of blood that's flowing through this, and, and the device itself is kind of churning the blood to pump it. Okay. You're just kind of asking the blood to clot. So eventually, no matter how much blood thinners and stuff that you take, if you kind of stay hooked up to a device like this for a long time, and long time, I mean like years, it's a complication is bound to happen. So something like this, it's not designed for long-term use, but it can provide, a temporary fix. Okay. And so this happens a lot because if you do have like a failing heart, it is possible for you to get a heart transplant, to get a heart that can, that'll be a lot more healthy. But a lot of times it takes a really long time for a suitable heart to actually show up that they can actually put inside your body. Okay. And so if you do need to get a heart transplant, you're usually on a waiting list for a really long time. Usually, hopefully it's on the order of months, but it can be on the order of years. And so during that time, to kind of help kind of support your circulation, that's what a VAD is supposed to do. Okay, but again, it's not meant to be a long-term solution. Okay. And so because this kind of hooks up directly to your heart, it is a big deal. And so even just to get the device in place, you need to get a fairly invasive surgery. And so there's a lot of risks associated with this as well. Okay. All right, and so the one that I'm showing you here, and so I know for the pacemakers they have that induction charging, but for a lot of the LVADs, they're usually charged externally because they require a lot more power than pacemakers. Because pacemakers are just like a tiny little pulse, and so the battery in there can last for a very long time. Because you have a pump, and probably a lot of you have worked with pumps, maybe as part of a fluids lab, they kind of eat up a lot of power. And so, you can't, it's usually not that safe to be kind of putting a lot of power through induction into your body. And so usually they have some kind of external power source here. So this person is wearing them like overalls. And so they have the batteries that are strapped on the outside here. Okay. All right, so let's talk some complications. Okay. And so, it's kind of a broken record at this point, but the primary concern with these kinds of devices is blood clotting. Okay. And it's especially concerned with VATS just because of how many moving parts and kind of how thin the passageways are. And so, it's something that doctors monitor very constantly. And if you're on a VAD, you basically have to be on blood thinners 24/7. Otherwise, it's a big risk of clotting. Okay. And because for these kinds of devices that are shown here, you kind of have wires that kind of come out of your body. You kind of almost have an open wound all the time. They try their best to kind of patch it up with band-aids and stuff. But anytime you have something that's coming from inside your body out, then bleeding and infections are going to be a concern as well. Okay. And so there's a lot of risk and complications with these VATs. And so that's why they're not supposed to be a long-term thing. They're just a temporary fix for a while. Okay. Okay. Any questions on VATs? Okay. Okay. And so the last slide I have for today, it talks about regulation. Okay. And so I have this slide here, just to kind of make you aware of it. But from what I hear, from people that work in the industry, this is a big concern, or not a concern, but it eats up a lot of your time as an engineer, because what I've heard from people is that you spend a lot less time designing the devices, and you spend more time kind of fighting the government regulators to convince them that your device is safe. But it's important, because these devices, a lot of them are considered by the government as safety critical devices, right? And so what that means is that the failure of this device can lead to significant harm or death of people. Okay. Think of the device that we just talked about, right? And so for ventricular assist device, right? If that VAD just kind of stops working suddenly, right, then the person's dead, right? And so they no longer have a means to pump blood in their body. And so it's really important that these devices are really fully understood by both the engineers and by the regulators, and that all the measures are taken to make sure that there's fail-safe so that these don't fail in a critical time. Okay. And so in the US, the primary government agency that's responsible for regulating these is the FDA. Okay. The FDA does a lot, and so they have a lot on their plates. Okay. And so if you develop a new device, or even just like an improvement or an optimization on a current device, it has to go through a very rigorous approval process. And you have to really show that all the risks and complications are known and minimized as much as possible. Okay. But with that said, as with anything you do in this world, it's impossible to eliminate all the risk. But it's important to, first of all, be aware of the risks that can happen and to minimize them as much as possible. Okay. And so this is actually, I've only kind of just heard about this process just from just talking just kind of casually to people. And so I'm really hoping that I can get my friend to come give a talk, because I really want to learn more about this process, because it's something that it's interesting, because I've talked to people on both sides, and it's usually a very contentious relationship between the engineers and the regulators, because they both kind of don't like each other, because they kind of see each other as kind of getting in the way of each other. So and so I do want to learn more about this, because it's not something that I have a lot of experience with myself. Okay. All right, any final questions on any of this? Okay, all right, so that's the end of the slideshow, and so that's all I got planned for today. And so we'll call it a little bit early today. And so on Thursday, we're going to start a new topic, which is 1D blood flow patients. Okay. All right, so thank you everyone for tuning in today. Hope you guys enjoy the rest of your afternoon, and I'll see you guys on Thursday.
You Dr. Trey.
Thanks, guys.